All right, so today we're starting with Hilbert spaces, and so we'll start. We will work on R. Yeah, that's a choice because, but in the last section we will discuss also the case where K equals C. All right. So first, so if you want to define a Hilbert space, the essential property of the Hilbert spaces is the product scalar, right? Scalar product. So scalar product is defined as follows. It's so H is a linear space. We assume here that it's over R, as I say it again. And so a scalar product is a bilinear function, meaning that it's linear with respect to its two variables. So it's from H times H into R, and you have symmetry and positivity. So this defines a scalar product. So we start with an exercise is a classical inequality, and so it's the Cauchy-Schwarz inequality. So you should have seen this inequality before, for example, in R to the n. And so it's just an exercise to prove it. So try to prove it. Oui, c'est pas obligé à Lyon, ça dépend. On peut dire aussi produit scalaire. Voilà. Mais effectivement, c'est ça. OK, en fait, c'est classique ça, hein. C'est très classique, donc faut le voir au moins une fois. Donc on va le faire. Ah, j'avais. All right. So this is a classical proof. So what we do, so we will write that. So let's look at this thing, U plus lambda V. So U and V are in H, right? So by definition of a scalar product, this is non-negative. And in fact, it is zero if only if V equals or U equals minus lambda V and this is for only one lambda. So okay, but so since this is non-negative, and I can develop with respect to lambda, so I obtain lambda square V. Thanks to the linearity and to the symmetry, I will obtain 2 lambda UV, and finally plus, this is VV, plus U. This is non-negative. But if you consider it as a polynomial of degree 2 in lambda, you know that necessarily the discriminant will be non-positive, because if not, you will get values for which this is negative. So since, let's call it P lambda, since P lambda is non-negative, you get that. So the discriminant will be 4UV square minus 4VVUU. So you get that 4 square. All right. And so this gives you U square less than U. VV, and therefore U V is less than. Okay, so now we will set we'll use this notation, and of course I ask you to prove that this defines a norm on H. All right, so to prove that this defines a norm, we need to prove these 4 points. So all the three, so the first one, the second one, and the fourth one are straightforward. Okay, I'm not going to do it. I'm going to prove the sub-additivity here. So if you look at, let's look at u plus v square. So this is u plus v, u plus v. And so this is u square plus uv plus vu plus v square. But by symmetry, this is u square plus 2uv plus v square. And so now here I apply the Cauchy-Schwarz inequality, and I obtain here, and I obtain that this is less than 2uv plus v square. So finally, I obtain my result because this is u plus v square. So taking the square roots, we obtain u plus v is less than u plus v. All right, so now, what's a Hilbert space? It's a linear space which, with endowed with the scalar product, is complete with the associated norm that we just defined. All right. So there are a lot of classical Hilbert spaces that are very useful. For example, so you have the Rn, L2, H1, the Sobolev space. Okay, in fact, Hilbert spaces are reflexive, but we are not going to we are not giving the proof here. Okay, so next, I propose you just to check very quick this equality, which is known as the parallelogram law. And it will be useful in the forthcoming for the course. It will be useful just after for a proof. So okay, try to check that it's straightforward. So so let's look at a plus b square plus a minus b square. So this by definition is, so a plus b plus a minus b, So this gives 2a square, because then I will get 2b square, and the other cancels because I will get 2ab minus 2ab. So I got that. Okay, next we have the theorem. So this theorem is also well known. It's important to know it and it's about the projection onto a closed convex subset of my Hilbert space. So this has a geometric, it's a really a geometric interpretation. So we will draw after, but so it says that for all u in H, you have some u star that will in K. So in fact, this inf is a minimum. So the u star, the distance between u and u star minimize the distance for between u and v for all v. Okay, so you have a u star in K, which makes the minimum of all of all the v's in K. And furthermore, you have that u star is characterized by this inequality. All right, so this theorem is really a geometrical theorem. And so the geometry of that is the following. So let's assume you have a convex K here. So I don't draw everything, but, and then you have a U here. And so the theorem just says that you have a unique U star here, which minimizes the distance for all v in K. And effectively, then if you take the scalar product here, for any v, this is this angle is more than p divided by 2, which corresponds to a negative scalar product. All right. Yeah, it's the projection theorem, yes, on the closed convex subspace. Okay, so we will we'll give a proof of that. All right, so we are going to prove that yeah, does exist a U star in K such that U minus U star minimizes is the infimum of U minus V for V in K. So for that, we start with, first of all, let D be this number. So I do again some so this is a number because this is positive, so this is a number, and so I can find a sequence that Vn be a sequence in K such that so U minus Vn converges to D. I can always do that by definition of the infimum. All right. So the trick to prove the existence of U star is to prove that Vn is Cauchy, because by assumption H is a Hilbert space. And so to prove that that Vn is Cauchy, we will use the parallelogram law. So let's apply the parallelogram law to U minus Vn and U minus Vm. Okay, so let's do that. So I will write that. So here I write the sum of A and B. I get 2 minus Vn plus Vm. And plus, now I will write, so this is A plus B, and I will write A minus B. So I get Vm minus Vn square, and this is equal to U minus Vn square, but 2 plus 2 U minus Vm square. All right, what's interesting here is that now I got here the norm of Vm minus Vn to the square, and it's interesting because I want to prove that Vn is Cauchy, so that's good. So I'm putting that alone, and so we have that Vm minus Vn square equals to U minus Vn square plus 2U minus Vm square minus minus 2 or 4 U minus Vn plus Vm divided by 2 square. All right, now, so I can say something about that. What can I say? Well, since K is convex and UN and Vn and Vm are both in K, so is Vn plus Vm. So this here, this term belongs to K. So I can say that this here, so this is less than G squared. And if I multiply it by minus, it will be greater. So finally, I get that Vm minus Vn square is less than 2u minus Vn square plus 2u minus Vm square minus 4u minus Vn plus Vm divided by 2. Yeah, so next, so I applying this this equality, we obtain this equality, and so we have Vn minus Vm square here, and since this term here belongs to k, I know that this term here is less than d. So if I multiply by minus, it will be greater. So finally, I obtain this estimate, and now the right-hand side converges to 0. So we have that Vn is a Cauchy sequence. So it converges to some u star, and finally we have the result.